Good evening. Today we are moving into the last chapter in our second textbook, that is chapter 8, Electromagnetic Waves. So, in the sixth chapter, we learned Faraday's law, which says there is an induced EMF whenever there is a change in flux. Induced EMF given by minus d phi by dt, which is minus d by dt of flux, as you know, is B dot A. So here, whenever we have a changing magnetic field, we will have an induced EMF. An induced EMF is potential difference, which means you need to do work to carry a unit charge. The work done to carry unit charge from one point to another point is what you call as this potential difference, which is the induced EMF. So since we have to do work, which it means that there is an electric field. So whenever we have a changing magnetic field, it will induce an EMF, which means in turn it has an changing electric field. So basically, a changing magnetic field can produce a changing time varying electric field. Now, symmetry in nature, you can find so many examples around us which follow symmetry. Like you have two ears, you have two eyes, and so on. So Maxwell predicted that there should be a counterpart to this. That is, if a time varying magnetic field is able to produce a time varying electric field, he predicted that a time varying electric field should also be able to produce a time varying magnetic field. In order to study this, we look at the case where we have the capacitor, the plates of a capacitor. Let's say we have a capacitor which is connected to, you may connect it to a DC source or you may connect it to an AC source. If it's an AC source, it will provide a time varying current which will charge the plates. Here, when you switch on the key, there will be an increase in the charge on the plates while the capacitor charges. If you switch off the key, then while the capacitor discharges, there will be a decrease in the charge on the plates. So basically, you may connect a source of AC voltage, or you may connect a DC source with a key, so that as you switch on and switch off, as the capacitor charges and discharges, the charge on the plates is either increasing or decreasing. Now the electric field we know is directed from the positive plate to the negative plate. It is given by E equal to sigma by epsilon 0. This we learned in the second chapter, where sigma is called the surface charge density, which is the charge per unit area on the plate. So I may write sigma as charge for unit area Q by A epsilon 0. So whenever you have connected it to a AC source which is continuously changing, or if you are switching on or switching off while the capacitor plate is charging and discharging, you know that the charge on the plates is varying with time. So because there is an electric field, we know there will be an electric flux which I denote as E here. This electric flux from the first chapter we know is equal to E dot delta S. Delta S being the area of the plate. So I may write this as E dot A. E dot A is EA cos theta. Theta being the angle between the electric field and the area vector. So if you have a plate here, the electric field and the area are in the same direction, cos 0, and so I may write it as E into A, which is equal to E, I'll substitute as Q by A epsilon 0 into A. So you see that the electric flux between the plates is simply Q by epsilon 0. Now, as long as the charge on the plate is a constant charge, then the flux between the plates do not change, the electric flux. But as you switch it on or switch it off, as the capacitor charges or discharges, this charge on the plate is either increasing or decreasing with time. It's a time varying charge, which therefore will change the flux between the plates of the capacitor. So this I may write as d phi E by dt, rate of change of the electric flux dt, will be equal to 1 by epsilon 0 dq by dt. This dq by dt, as you know, is the current, which Maxwell called the displacement current. And so this displacement current ID is epsilon 0 d phi E by dt. He called it the displacement current because it is the current between the plates of the capacitor. You know there is current in the conductor here, which we call as the conduction current. The conduction current is due to the movement of electrons in the conductor. The movement of electrons will constitute this conduction current. But between the plates of the capacitor, we know there are no charges that are moving, and therefore this current here between the plates of the capacitor is due to a change in the charge or change in the electric field between the plates of the capacitor, and this varying electric field or varying flux will give rise to a displacement current, and the displacement current will have a magnetic field associated with it. So what Maxwell predicted was that whenever there is a change in electric field, a time varying electric field will give rise to what you call as the displacement current, and if there is a current, we have a time varying magnetic field between the plates of the capacitor. And it was as predicted. When he kept a magnetic needle between the plates of the capacitor, it showed a deflection while charging and discharging. So the deflection on the magnetic needle is simply because of the existence of a time varying magnetic field. So what we conclude from this discussion is, in Faraday's law we know that a time varying magnetic field can produce a time varying electric field, and from Maxwell's conclusions about the displacement current, we know a time varying electric field can produce a time varying magnetic field. Now these magnetic field and these waves propagate in space. These waves are called the electromagnetic waves. So if you talk about a stationary charge, which we did in chapter 1, stationary charges do produce electric fields, but they produce static electric fields which are constant in time. Similarly, in the 4th chapter, we talked about magnetic fields produced by current carrying conductors. We have current carrying conductors, a circular loop, a straight conductor, solenoid, all of them producing magnetic fields, but they produce magnetic fields which are constant in time. So stationary charges or charges which are in uniform motion in a conductor cannot produce these time varying electric fields. They can electric field or magnetic field. They can produce electric and magnetic fields which are constant. So what we need here is an oscillating charge. So any oscillating charge is an accelerated charge. You have learned this chapter called oscillations in 11th standard. And in that chapter, you've learned that every particle that is oscillating about a mean position has an acceleration which is directed towards the mean position. So this, if you have an oscillating charge, which is also an accelerating charge, it produces an electric field that is also oscillating with time. And an electric field, according to Maxwell, this oscillating electric field will generate an oscillating magnetic field. And by Faraday's law, we know a changing magnetic field can produce a changing electric field. So they regenerate one another and propagate through space, and these waves predicted by Maxwell was called the electromagnetic wave. Maxwell also came up with a equation, wave equation, which included the velocity of this electromagnetic wave as it propagates through a medium, given in terms of two constants that we know, that is the permeability and the permittivity of the medium. So he said, he came up with this equation: velocity of a wave, the electromagnetic wave in a medium, is given by 1 by root of mu and epsilon, where mu and epsilon happen to be the permeability and permittivity of this of the medium. Now, if it is in free space or vacuum, we know this will be mu 0, epsilon 0, and we already know the values. So when Maxwell plugged in the values for mu 0 and epsilon 0, he got a value which is close to 3 into 10 raised to 8 meter per second, which is the velocity of light in free space or vacuum. And he came to the conclusion, or he predicted, that light is an electromagnetic wave because of this finding. It was in 1887 that Hertz first generated and detected an electromagnetic wave of low frequency range, and he was also able to prove that this electromagnetic wave that he generated experimentally had the same velocity, 3 into 10 raised to 8 meter per second, thus proving what Maxwell had predicted, that light is an electromagnetic wave traveling with a speed of 3 into 10 raised to 8 meter per second. Also, the oscillating particle, the charged particle that is producing this oscillating electric field and therefore generating an oscillating magnetic field, has a particular frequency, and the frequency of this charged particle, the source, will be the same as the frequency of this electromagnetic wave. So your electromagnetic wave has a frequency which is equal to the frequency of the source, that is the oscillating, that is the accelerated charge. The SI unit of frequency, that is Hertz, was given in honor of his, was named in his honor, this Hertz. Then we now need to go into the nature of this electromagnetic wave. So this electromagnetic wave, we know, has an electric field and a magnetic field. This electric and magnetic field are perpendicular to each other. Now I've drawn here an electromagnetic wave which is traveling along the z direction. So this magnetic field and this electric field are perpendicular to each other, and they are perpendicular to the direction of propagation of the wave. So you will see, you will have an electric field. So this, if this is the z-axis, and let's say this is a y and this is the x-axis, you will see you have an electric field that is oscillating in the y-z plane, and you have a magnetic field that is oscillating in the x-z plane, the two being perpendicular to each other and also perpendicular to the direction of propagation. So that is what we see here. This wave is traveling along the positive z-axis. We have the electric field oscillating in the yz plane. We have the magnetic field oscillating in the xz plane like this. Okay, perpendicular to each other. Then the next thing that I need to, so this is the diagram that you might be asked to draw, an oscillating electric and magnetic field, which is the electromagnetic wave traveling along the positive z-axis. Then the next next one that we need to discuss is, see, in the last chapter, waves in class 11, we learned the wave equation which was, so if we have a wave traveling, let's say along the x-axis, this is the y-axis, we represent, let's take up, this is the origin, let's take this as a particle here at some distance x from the origin. Its displacement along this is the y. So we represent the wave equation as y at xt equal to a sine kx minus omega t. I hope you remember this equation from last year's wave chapter. Now this represents the displacement of a particle which is at a distance x from the origin at a particular time, because this particle is actually oscillating or executing simple harmonic motion about this mean position. So at some position x, at some time t, the particle, if the particle's displacement is here, this vertical displacement from the mean position is represented by this y. This A stands for the amplitude. Amplitude means the maximum displacement of the particle from the mean position. That is what we call as A, amplitude. K, as you remember, I hope you remember, is called the wave number. Wave number, which is the number of waves in 1 meter of the medium, in unit meter. That is, let's say this is 1 meter. From here to here, this is 1 meter of the medium. How many waves are present in that 1 meter of the medium is what you call as this wave number. So naturally, if, see, this is one wavelength, right? From one crest and a trough together constitute 1 lambda. So if this lambda is large, then the number of waves in 1 meter will be lesser. If the lambda is small, you can have more number of waves in that 1 meter. So this k, which is called the wave number, is inversely proportional to lambda, or k is equal to constant 2 pi by lambda, which is represented, its SI unit is radian per meter. So k equal to 2 pi by lambda, and I may, if I multiply with frequency, top and bottom. This 2 pi nu you know is omega divided by lambda into nu, and that you know as C. I think you learned it in 9th standard. C is equal to nu lambda. So I may write this as C, or that is the velocity of light in air or vacuum. If it is in any other medium, we will represent it with letter V, velocity. So we have two formulas for K. One is the 2 pi by lambda, and where lambda is the wavelength, or the wave number K is equal to omega by C, C being the velocity of light, 3 into 10 raised to 8 meter per second. Also, this omega, you know, is the angular frequency in radian per second, which is equal to, as you know, 2 pi nu, where nu will be in hertz. This nu is the number of oscillations that this particle will make in 1 second. It's also the number of waves that will cross a particular point in the medium in 1 second. So, and also remember, if you see x minus, it means that the wave is traveling along the positive x-axis. But if you see x plus, then it means that the wave is traveling along the negative x-axis. This is discussed in detail in your chapter waves in class 11. That if it is x minus, your wave is traveling along the positive x-axis. X plus would mean that the wave is traveling along the negative x-axis. So now if I'm going to use this equation to represent the electric field and the magnetic field, the oscillating electric field and the magnetic field, you will see that the amplitude of the electric field I have represented with E0, and the amplitude of the magnetic field I have represented as B0. So I may write the electric field represented by at any instant, electric field is equal to the amplitude E0 sine K. Your wave we have drawn as traveling along the propagating along the z axis. So K is z minus, because positive z axis, omega t. And the equation for the magnetic field is, the amplitude of the magnetic field is B0 sine. This part of the wave function wave equation will remain the same, because we are talking about the same wave, right? Electric field and magnetic field of the same wave. So both of them are propagating along the positive z axis, the same wave number and the angular frequency. Omega is the angular frequency. Now, you need to know that the electric field and magnetic field, I said, is perpendicular to each other and perpendicular to the direction of propagation. So, if it is traveling along the z-axis, we have taken our electric field along y and the magnetic field along the x-axis. It could be the other way around too. You could have the electric field along the x and magnetic field along the y. So, this is the next property we need to discuss about the electromagnetic wave. The next property that I'm going to discuss about is the relation between this E0 and B0. We may write the next property as C equal to E0 by B0. If the electromagnetic wave is propagating in space, that is free space or vacuum, any other medium, this would be V equal to ratio of E0 by B0. This is nothing new to you, I think, because in chapter 4, if you remember, we did a topic called velocity selector, in which we have a electric field and a magnetic field perpendicular to each other, and the charged particle has a velocity perpendicular to this electric field and magnetic field, and we came to the last equation as V equal to E by B. So same thing we have, V equal to E0 by B0. Then the next property that you should know about this electromagnetic wave is that it does not require a material medium for its propagation, because an oscillating charge will give rise to an oscillating electric field, which will in turn generate a oscillating magnetic field, and they regenerate one another, and that's how they propagate through a medium. So they do not require a material medium to propagate, and that is why if you know that light travels from the sun and reaches us through vast regions of vacuum. So we can come to the conclusion that electromagnetic waves do not require a material medium to propagate. The next property to be discussed is that the velocity of this electromagnetic wave, light is an electromagnetic wave, is the velocity I told you is given by 1 by root of mu epsilon. In free space, this would be 1 by root of mu 0 epsilon 0. So all electromagnetic waves, the spectrum you will study at the end of the chapter, all of them will have the same velocity. In free space, they all travel with the same velocity, 3 into 10 raised to 8 meter per second. That is why in 10th standard, when you learned light, you would have learned as light enters a denser medium, its speed decreases. It's because as the medium changes, the permittivity, the permeability and the permittivity of the medium changes, which changes the speed of that electromagnetic wave. The last property that we need to discuss here is that these electric and this electromagnetic wave has energy, carries energy, and therefore carries momentum. See, in the second chapter, when we did capacitors, we derived an expression for the energy between the plates of energy stored in a capacitor as UE equal to Q square by 2C. Now this I call as UE because it is electrical energy. Since between the plates of the capacitor, what we have is an electric field, and the energy stored in this is called the electric energy, Q square by 2C. If you substitute for Q between the plates of the capacitor, we know that the electric field is Q by A epsilon 0. So I may write this UE is equal to Q square will be E square A square epsilon 0 square by 2 into capacitance. I hope you remember the formula as A epsilon 0 by D. By D, I took it on top. So if I cancel this and this, I have this as half epsilon 0 E square into AD. If we are talking about the energy density, which is the energy stored in unit volume, which we did in that second chapter, we know that the volume of a capacitor is plates. Let's say the capacitor, we have a plate area. We have two plates like this. The volume will be plate area into height. That is base plate area A into D. So, energy density here will be given by half epsilon 0 because you divide by the volume, which is area into D. So this is the energy density of the electrical energy density, which we derived in chapter 2. We also did the same thing in magnetic energy density in chapter 6, where we talked about the energy stored in an inductor. In inductor, we have the magnetic flux changing, and because of which there is energy stored. So that is called the magnetic energy, UM. We derived an equation as half Li square, where L stands for the self-inductance of the inductor. This is half Li square. So this L, we know we've derived this formula as mu 0 n square La. This again comes from the 6th chapter, electromagnetic induction, where for an inductor, the n square is a number of turns per unit length, L is the length of the inductor, and A is the area. I, for an inductor, we have a magnetic field B given by mu 0 Ni. So if I'm going to substitute these values here, we have Um is equal to half into mu 0 n square La. I square from here will be B square by mu 0 square n square. I may cancel this and this, and the energy density will be dividing this total energy by the volume of the inductor. Volume of the inductor is what? L into A, because base area into height. So if I take away this, I am left with half B square by mu 0. This is there in the 6th chapter. So now what you see is we have energy density for an electric field given by half epsilon 0 E square, energy density of the magnetic field given by half B square by mu 0. So that means an electromagnetic wave which has an electric field and a magnetic field has an energy associated with it. And this energy I will denote as U. Now what we are going to do is find an expression for the momentum of this electromagnetic wave. As we go into the next few chapters, we will be discussing how this light has dual nature. It showed certain properties which proves that it is a wave. There are also other certain phenomena which tells you that light also has particle nature. And as I think you already know that the particle of light is what you call as photon. So let's say we have a surface on which light is incident or electromagnetic wave is incident. Let this photon have to travel through a distance delta x to be absorbed completely by the surface. In which case, its momentum p, there will be a change in its momentum because its momentum will now reduce to 0. By Newton's second law, we know that the force is delta p by delta t, rate of change of momentum, where this force is the force required to bring the momentum of the particle to 0 as it is absorbed after traveling through this displacement delta t. So from here we know delta p is F into delta t. To substitute for this F, see what is the energy, change in energy when this happens will be force into displacement. So we have F into displacement, or F we know is delta U by delta X. So I may write this as delta U by delta X by delta T. I can bring this delta T down. Or this is equivalent to delta U by delta X by delta T is what? Displacement by time. For an electromagnetic wave which is traveling in vacuum or free space, delta X by delta T will be the velocity. So that is change in momentum. So we know that the momentum can be given by change in the energy by the velocity of light. Also, when this is incident on a surface, because it has momentum, it will exert a pressure which is called the radiation pressure. To find an expression for pressure, radiation pressure is, we know, force by area, which is force is delta P by delta T into area. So this is the radiation pressure, the pressure exerted by this electromagnetic wave when it is incident on a surface. So when the sun shines and it's incident on your hand, you feel the warmth. That is because every radiation carries energy. So you can feel the warmth, but you do not feel any pressure or any momentum imparted to your hand, simply because this momentum is here, this velocity of light is very large. Because of this, the momentum imparted is small, and if the momentum imparted is small, then the radiation pressure is also very, very small. That's why when sunlight falls on your hand, you can feel the energy, the warmth, but you do not feel any pressure, simply because of this large C. We have a very small change in momentum, and therefore we don't feel the pressure. So these are the properties that we have to discuss under electromagnetic waves. We have a whole spectrum of these waves. Microwaves, you need to study about microwaves, gamma rays, infrared, visible light, ultraviolet, radio waves. All these we will be discussing in our next class, and I will be sending you the properties of all these waves as PDF file. Okay, thank you and good night.